welcome to the fabulous world of the density matrix. It's for the moment it's going to be the last video that I make about density matrix, but I think it's been because one of the things that I realized is that there's going to be there's no sort of standard way of how do you approach building an algorithm from scratch, like a problem that nobody else has ever solved before. How do you debug? So sort of general tooling and good practices for quantum programmers. And I had the intuition, I had the feeling that the density matrix was one of those things worth taking a look at, because it's like when you Google density matrix, you've got a bunch of um, physics explanations and interpretations and things that the density metric means and it doesn't mean. And some of those things are a bit esoteric. Some of those things seem a bit more practical. And in the past videos in this series of the density matrix, I've been exploring some ideas, but nothing was really clicking until today. I kind of had that moment where I thought, I had been reading stuff about something called partial trace of a matrix, which then I kind of realized that is definitely a really useful application of the density matrix. So, and what this means is, and so what I want to show in this video is that you've got this matrix here, which is nothing else than another way of representing the overall state of your system. But this actually becomes pretty useful when doing two things. So when you're building a circuit or building sort of an algorithm that has more than one qubit, I mean even more than two or three, because with two it's still easy to do. And even when you're debugging and you want to understand parts of your overall system. So you probably have realized and have come across concepts or algorithms that talked about Alice, Bob, Charlie, and sort of different systems put all together, or people holding different qubits and whatnot. Things that, like, if you stay with this tool when you're programming, right? Let's say, for example, that you want to have a system where, I don't know, this Alice, Bob, and Charlie, and each of them have two qubits, right? Just whatever. I'm just making this up right now on the spot. So you would have six. So you would have six qubits, right? And so this. Okay, six is probably not a good example. Let's say four. I mean, you could even let's say Alice has one, or it's Alice and Bob. Let's just make it simpler. Alice and Bob, and each of them have two, right? So the issue is, when you're building the algorithm, you might want to, for a second, focus on certain properties that only appear, or that only need, or only make sense for Alice, for example, right? And say the qubits 0 and 1 are only relevant for Alice. And so you want to make sure that that subsystem, right? Let's call that a subsystem, has a certain state, or has a certain, because the problem with quantum computing circuits and programs, if you compare them to classical ones, is that you cannot just easily move up and down your like modular structure to say I have a whole system and this system is composed of subsystems, and then I can just quickly talk about each subsystem and the system overall being the sum of its parts and whatnot. It's a bit more complicated, because when you have something like this, right? And this is, let's say, this is Alice and this is Bob. So this is Bob here. If you have something like that, right? Let's just put some Hadamard gates in here, maybe an X and a Hadamard gate, another one maybe here, and then you want to do things like that, and you're doing fancy things like these. I don't know if that's even doing anything. Whatever, it doesn't matter. But so you can't, so you can understand the whole system. If you take a look at this, right, you see sort of the whole system, all the possible states and whatnot, but you cannot easily say, okay, what if I just took the Alice system? How can I make sure that I can use, or how can I make sure that Alice has, for example, while I'm building the algorithm, a system that is in a perfect superposition? Just as an example, those things are complicated to do. So, and this is where the density matrix comes in super handy. So you see here, you've got a real component, so real matrix, and a complex matrix. But let's just focus on the real one, because I think it's going to make the explanation easier. Um, the idea here is, if you take a look at all the trace, and this is a mathematical concept, but it's not really mathematical in the sense that the matrix is just you're just putting all the possible states against each other, right? And then um, the diagonal of the matrix tells you what are the probabilities of the whole system being measured in each state. So I think I talked about it in the first video of the density matrix. But a really cool property about this representation is that you can easily, it's not that easy maybe to do this by hand. You can do that easily with when you have 2 qubits, and maybe I'll just come back to a 2 qubits game so I can showcase that. Just going a bit slow right now, but so let's just go back to what we had, and we had this, and then I'll just put something. This doesn't have any meaning, it's just random stuff. And let's get back to 2. So the density matrix is a bit easier to handle now. So there is something called the partial trace of the matrix that you can do to understand what's the state that each qubit or each subsystem is in. So in this case, for example, and you can Google that. I'm not going to really go into this, but if I was checking recently, partial trace of a matrix, and I think you can, even if you Google the images, you've got some really graphical explanations. For example, for the second qubit, you can just, so this is the partial trace. So you just do this plus this plus this plus this, right? So in this case, this means if you do this plus this, right? This is 0.25, 0.25, that's 0.5. This plus this is 0, right? Because they cancel out. This plus this. This plus this is, again, 0.5. And this plus this cancels out. So that literally leaves you with a matrix that it's like, I'm going to paint over this right now. It basically leaves you with 0.5, 0, 0.5, which means that this actually describes you that system. The system, sorry, I think that was system Q, the with the second qubit. It means that if you take a look at that particular qubit, it's going to be 50% 1, 50% 0, independently from the other one. And that's really useful because you could use this while building an algorithm. Maybe you want to reuse a qubit, right? And then but you want to make sure that that qubit still is in that subsystem, or qubit is still in that state, because you want to use it as a control qubit for something else. So you really care about that. So this is a really particular practical usage of that, which I think at some point in time I'm going to probably shift to actually try to solve some problems live and really build some algorithms from scratch, and then see what kind of tools become in handy for those types of problems. But this is a really particular example of how the density matrix can be used to help you analyze that. Because when this is easy to see, when this grows, it's a bit more complicated. Now the tooling, the IBM tooling, is not perfect for that, in the sense that you still got to do the manual computation. It would be really cool if you would be able to see quickly, with the click of a button or something, kind of see the partial trace or the partial matrix of each of you, or a particular subsystem. That would be really interesting, because that's going to help. That's definitely helping you to build an algorithm. So far, everyone's focused on analyzing existing algorithms and trying to figure out how do they work. But we have to move away from that into a world where we start thinking about what's the tooling that a quantum programmer needs to build an actual quantum program. Even from an intuition perspective, without really having to dive into the mathematics initially, because we want to get stuff practical for the industry, right? So I think that's an interesting perspective. I think that the density matrix, you can do a lot of other stuff with this. I've read some papers where they build up a measure of correlation, and build up a measure of how much entangled the system is by doing some stuff with the off diagonal or the non-diagonal elements. But those things are, maybe I'll explore them one day. But I thought that was a really practical use case. I hope that's useful. I hope that gives you because not. I think there's no other quantum computing interface out there yet that gives you that out of the box, which is really nice because you at least have the matrix and you can visually see, oh, those things cancel out, those things cancel out. So you can visually see that still, it gives you a feeling of, okay, that particular subsystem is in that superposition or stuff like that. So I think this is definitely an interesting topic to put to use, but we'll see if we can put it to use with an example at some point in time. Perfect.